Thanks so much for that introduction, Sam. It's a real delight to be here, and a particular honor and privilege to have been named as part of the Scientific Advisory Board of Mātai. It's truly amazing opportunity for me to do this. So I want to talk about perhaps a little bit different theme. Now, this is sort of unlocking possibilities of cutting technologies, but maybe not costing as much as some of the high-tech equipment that we often think of as high-tech imaging. So I'm from the Robarts Research Institute in London, Canada. Who knew that there was a London in Canada? For those who don't know quite where it is, it's about 200 kilometers west of Toronto and 200 kilometers east of Detroit and just over Lake Erie from Cleveland. The Robarts Institute is on the campus of Western University and is right next door to a large teaching hospital. Mātai reminds me of Robarts 35 years ago when it started off as a very small medical imaging research institute with one MR scanner. Sound familiar? Now we have 5 MR scanners in that research institute, everything from 3 Tesla and 7 Tesla human to 9 and 15 Tesla animal scanners. It's also a great pleasure for me to know that one of my recent graduate students, Dr. Loxland Kasa, who originally comes from Papua New Guinea, is going to be coming here to Mātai to join the team within the next couple of months. So let me start with my research focus. I've been working in image-guided interventions for a long time. If you can't see it, you can't hit it. If you can't hit it, you can't treat it. And the other thing that we like to use, the statement we like to use to guide the rationale for image-guided interventions is surgery as a side effect of therapy. We often hear of people having a hard time recovering from surgery. They're not recovering from the therapy, they're recovering from the intervention getting to that surgical site. So if you can minimize that sort of intervention, we're doing a lot of good for the patient. Let me give you let's start off by looking at what high-tech imaging we all have available to us now, and it's been an amazing journey to see this evolve over the past 50 years. We have MRI and CT for diagnosis and planning surgeries. And as Dan and Hamid pointed out, if we're using these images for surgical guidance, we need to register them to the patient. And clearly, things move between imaging and the patient being on the operating table. So we almost always need some sort of intraoperative imaging as well. I should point out that it is possible, theoretically, and has been technically demonstrated, that you can do surgeries in CT scanners and MR scanners. It's very expensive, very impractical, and it's not ever going to be a mainstream approach. Let me give you an example of one of the projects that we've been working on that perhaps uses some lower level of technology. Still high tech, but not as expensive tech. One problem that we were asked to solve a few years ago was image guidance for repairing a flailing mitral valve leaflet. And you can see on that video on the right that involves an instrument going up through a hole in the heart, clasping onto that valve, tying a little thread onto it, bringing it back to the apex. And this has been guided by ultrasound. The image you see on the left is an ultrasound image that's obtained from a probe that's placed in the esophagus looking at the heart from behind. And you see 2 images there. These are 2 images that are actually at right angles to each other. And so we wanted to improve the way that the surgeons approach this problem. If we look at the trajectories of 5 different cardiac surgeons getting that probe from the apex of the heart into the mitral valve area, we see that the pathways look like spaghetti. They're going all sorts of places inside the heart and places where they shouldn't really be going. So this led us to take a new approach where we integrated ultrasound and augmented reality. We built a system using the same imaging data, but using the display that we see on the right, where we can track the instrument both in terms of how far away it is from the target and how far off center it is from the target. And when we tracked the trajectories of all of the same surgeons, we got a trajectory that looked like the, or trajectories that look like the image that you see on the bottom right. And this turned out to be much, much better because it restored the hand-eye coordination of the surgeon, which is a huge deal when you're talking about minimally invasive interventions in image-guided surgery. If what the surgeon is doing is disconnected from what he's seeing, it gives him a lot of trouble. So this resulted in a technique that was 4 times faster and 40 times safer than the previous standard of care. But this success also led us to think about more general terms about doing more with less, or frugal technologies. Maybe I should call them accessible technologies, because sometimes frugal seems to mean that you're taking shortcuts, you're skipping out steps. That's not what it means at all. But whether it's frugal or accessible, it's designing a technology from the bottom up that can do the job, but not be the all-singing, all-dancing system that some imaging and surgical techniques use. So we're looking for a substantial reduction in cost, concentrate on the core functionality that's required for a procedure, and then optimize the performance levels for that particular procedure. Recognizing the value of frugal technologies, the biomedical engineering school at Western University has recently embarked on a formal frugal innovations program, and we're interacting with Indigenous communities in Canada as well as communities in Africa to partner with them to build technologies that can directly affect healthcare in these settings. I won't go over this table, but it just basically says, instead of top-down building a $5 million machine that can do everything, we start from identifying a problem and build a system using local resources from the bottom up. And this can result in much greater accessibility to technology in under-resourced settings, and can be achieved at much less cost. Now, the point I want to make is that cutting-edge technologies need not be expensive. And we have many tools available to us. 3D Slicer is one particular imaging platform that's been developed over the years that's become ubiquitous. The Mātai artificial intelligence framework, again, built by researchers in the field and made widely available. Point-of-care ultrasound, or POCUS ultrasound. Instead of a $300,000 machine, point-of-care ultrasound can be available for several $1,000s. And augmented reality, you've seen lots about augmented and virtual reality. Augmented reality can be part of this accessible, cutting-edge technology, or group of technologies that can be used to build systems that can benefit these communities. So 3D Slicer, for example, was conceived by a good friend of mine, Dr. Ron Kakinis, a radiologist from Harvard Medical School, 25 years ago. It's grown, the community has embraced it. It's had over $50 million of funding since 1998. It has many, many functions, tons of global developers continuing to build the system. And the unique feature of it is that it's curated by a professional software company that makes sure that every contribution to it is robust and stable and is not going to cause the system to break. And it is sufficiently robust that the core of 3D Slicer can be used for commercial applications. Point-of-care ultrasound, instead of a big cart with big screens, the whole ultrasound machine can be this little handheld device that can communicate with a laptop, a tablet, a cell phone, or communicate with the cloud. And artificial intelligence has had a big role in making this type of technology available in such a small footprint. POCUS has the functionality of many, much more expensive ultrasound machines, but it has this very, very small footprint. POCUS has many applications. It can image the heart, can image the lung, image the abdomen, can image vessels to show the doctor how to put a catheter into a vessel, and it can even look at bone fractures. There are pros and cons of ultrasound, POCUS in particular. On the plus side, it's real-time, it's inexpensive. It can be 2D, it can be 3D, it can be dynamic. And you can use it simultaneously for both imaging and tool tracking when you're performing a procedure. Ultrasound is perfect for detecting the deformation of tissues during a procedure. And so it's ideal for image-guided interventions. The downside, it's highly operator dependent, and images can be very difficult to interpret. Ultrasound doesn't pass through air, and it gets blocked by bone. So it's very difficult to see on the other side of the lung or on the other side of a bone. But nevertheless, it has all of the previous uses that I mentioned. Now, why is artificial intelligence important in this whole story? Well, it hasn't been around for that long, but it's been around for long enough to demonstrate that we can use AI for improving the overall efficiency of many procedures, both in diagnosis, interpreting images, identifying abnormalities, and providing decision support for clinicians. So overall, the use of AI has been shown, much to the surprise of many, to be effective in better patient care, allowing for fewer errors to be made, and improving outcomes for patients. I mentioned some of the downsides of point-of-care ultrasound. And one of the biggest downsides is getting the operator more familiar with what's going on in the ultrasound image, how to train the operator, how the operator can make sense of the image. And artificial intelligence has already been shown to help in many ways. It can help automatically classify images, relate images to the target anatomy, guide the operator to the regions of interest, and generate measurement data, and reconstructing in general three-dimensional images of the anatomy. But one thing about artificial intelligence is that it needs to be trained on data. And this is one of the big roadblocks for artificial intelligence, but fortunately, the global community is providing more and more open source data sets that can be used to train these systems to make them effective. What about the role of virtual and augmented reality? One of the most obvious ways is to see inside the patient's body. Take that MR or CT scan that the patient's had and put it into an augmented reality device and be able to allow the surgeon to see what's inside the patient's body. You can see that on the image on the screen. Also, augmented reality can provide virtual screens in the operating room. Instead of multiple large, heavy displays, we can have no displays in the operating room and just bring them up at will and place them where we want them to be in the operating room. And all of these areas can help provide a much better interface between the surgeon and the patient during these procedures. One of the really cool things about 3D Slicer is that with about 20 lines of code, you can build a basic ultrasound-guided intervention system right out of the box using this platform. And so let's think about how AI and augmented reality can be used to minimize the barriers in point-of-care ultrasound. You can think of an operator wearing an augmented reality headset and having it display the images the ultrasound images within the patient's body and suggesting whereabouts next to scan to optimize the scanning procedure. Another area where augmented reality and artificial intelligence can help is reconstructing three-dimensional images of structures in the body as the operator is scanning them. And you can see the carotid artery being built up as the operator is scanning that ultrasound probe. I just want to end up with a couple of examples from a very good friend of mine, Dr. Gabor Fitchniger from Queen's University in Kingston, Canada, also in Ontario. He's already been engaged in a number of projects in Eastern Africa using 3D slicer and POCUS to address very real needs in countries like Mauritania. And even in this particular example, they started off using a commercial add-on to this ultrasound probe that consisted of a needle guide that would allow the needle to be tracked to go to a point that could be seen in the ultrasound. But even this at $25 a pop is too much for certain under-resourced communities. So this group from Queens built this system for 25 cents that consisted of a 3D printed piece of plastic with the appropriate needle guide built into it, and used a simple surgical glove as the sterilization barrier between the ultrasound transducer and the patient's skin. So you can see, just with taking this minimally invasive, this frugal technology approach, you can save 100 times the cost. Another project has been in Senegal, where they've used an atlas of the prostate to guide prostate biopsies in much the same way as we were shown yesterday. This is not using the preoperative images registered, but using a 3D atlas to help guide the operator to the appropriate point to biopsy. So in conclusion, I just want to emphasize that much of the world can't afford high-cost technology, but we have the resources to change all of that. It's going to require a low capital investment, and I think we as a medical imaging community have a duty to exploit these technologies to enable wider access. So with that, I'll just acknowledge the incredible support of all of the students I've had over the many years and all of the funding opportunities that we've had to allow my work to have continued over these past 40 years. So thank you very much. You're all right.